Hello everyone, my name is Tianyu Kang. Today, I'm going to introduce a novel deep learning model by stacking conditional restricted Boltzmann machine and deep neural network. This is an interdisciplinary research between University of Massachusetts Boston and the Harvard Chen School of Public Health. This research is not only working on machine learning part, but also on a very complex real-world data. My presentation will mainly in four sections. The first one is introduction and motivation. The second one is introduce our overall approach, stacking condition restrict one's machine and deep neural network. The third section will talk about a very key point in the second section, how to modeling domain knowledge into feature-feature relation. Finally, we are going to show some real-world experimental study in both supervised learning and unsupervised learning. This program will include clinical trials, cancer, and high school quiz. Let's start with a figure of our model structure. If you are familiar with machine learning, you will find the part in the blue blocks is the deep neural network. Deep neural networks are data-driven machine learning approaches, and the part in the red box have sparse connections. In our model, how neurons connected are based on the domain knowledge. So that's basically a model-driven approach. As we know, machine learning has briefly two approaches, data-driven and model-driven. They have both advantages and disadvantages. Data-driven approaches are very powerful when we have sufficient data, but it also needs data to be comprehensive. In real-world problems, data are not always abundant. Sometimes they are scarce and expensive. For example, in cancer study and clinical trial programs, data could be very rare. In those situations, integrate model-driven idea could be a good solution. It can make up the shortage in the data-driven approaches and make the data collection become easier, and also make the model achieve higher performance. Of course, that's not a clear task, but there are already some approaches combine data-driven and model-driven approaches well. For example, in convolutional neural networks, the convolutional layers take advantage from feature spatial relations between pixels. In a picture, the location of pixels have naturally spatial relations. Another example are recurrent neural networks. They take advantage from feature temporal relations. Because some data are in a time series, they have natural temporal relations between the data which in the near time steps. Our approach takes advantage from feature-feature relations. In the following section, I will introduce the overall structure of our model. First, we have an input layer, then we connect it to a hidden layer with sparse connections. The sparse connections here are not randomly decided. What we do here is construct a bipartite graph, and the connections in the bipartite graph represent the feature-feature relations. In other words, these two layers can be considered as a conditional restricted Boltzmann machine. Because in real-world problem, we will have very little data, so we further add a cycling structure to enlarge the information we gain from this structure. Then we stack in this conditional restricted Boltzmann machine with a deep neural network. This deep neural network could be any deep neural network we already have. It could be a multi-layer perception neural network for supervised learning problem, or an autoencoder for unsupervised learning problem. We also add feature-feature relations into the deep neural network part as forms of regularization. Now I want to further introduce a mathematical concept in the conditional restrict Boltzmann machine part. Let's call the input value AU0 with the weight WUL, which is the weight between the upper level and the lower level. With some coefficient alpha, then we can easily get the value in the hidden layer, alpha WL AU0. Then we pass the value in the hidden layer to the cyclone structure, then pass back. Finally, we can get the formula in the bottom of the slide. ALT equal to alpha WLAUT plus 1 minus alpha AL0. Here we call alpha the smoothing parameter, which is a coefficient to choose how many information we want to get from the cycling structure and how many information we want to get from the original input. WL is a sparse matrix representing the feature-feature relations. Mathematically, Wij will equal to some real number if AUI co-occurrence with ALJ. Otherwise, it will equal to 0. Notice t here is the iteration number. When t goes to infinity, ALT will converge to a stable number. But in our experiment, t not necessary to be very large. Usually, in our problem, we just set t equal to 5. That's for conditional restrict Boltzmann machine part. Then we want to talk about how we integrate feature-feature relations into the deep neural network part. In any kind of neural network structure, we can choose some layers which we already know the physical meaning of the neurons in the layer. Usually they are output layer, because the output layer have a clear physical meaning which represents the class labels. Then we can apply bipartite graph-based realizations to the connections which connect to that layer. We will introduce how to modeling domain knowledge into a search bipartite graph in the next section. Here we just introduce the mathematical formula behind it. The regularization we use is trace H L alpha H transpose. Here, H stands for the hidden layer connected to the output layer. L alpha equal to G minus ADJ. G stands for graph Laplacian. ADJ is the adjacency matrix defined by the formula. This adjacency matrix is considering nearest neighbor defined by a special formula shown in the bottom of the screen. Let's move to the next part, how we modeling domain knowledge, how we extract feature-feature relation. Usually, those kind of feature relation information are very hard to put into our models. Our approach is modeling this feature relation information into a standard bipartite graph. Here we give examples about how we modeling two most common type of feature relation information into a bipartite graph. The first example is about direct relations. Here we have an example of that kind of relations. A point to B means B is dependent on A. Based on the example here, we can see there are different types of features. Some features are going to change other features, and some features are influenced by other features. And some features stand alone with themselves. Then we put all the features which are going to change other features and the lonely features in the first part, and all the features in the second part. The features in the first part and second part have a connection as long as some feature in the second part is dependent on some feature in the first part. A special point is a feature appear in the first part is going to connect it to itself in the second part, because we don't want to lose any information. For example, A1, which on red line, is a feature which is going to affect the other features. So it appears in both first and second part in the bipartite graph. And A1 is going to affect B3 and B4. So in the bipartite graph, it has connections to B3 and B4. Also, A1 have a connection to A1 itself in bipartite graph. And because B3 is dependent on A1, so it is only connected by the bipartite graph, and it only appears in the second part in the bipartite graph. C1 is a lonely feature, so it appears in the both first and second part of the bipartite graph, and it only have a connection from itself to itself. This is direct relation case. Another example is about features have statistical coherence. Some features may don't have any direct relations, but by the domain knowledge, we know some features may share the same concept. These concepts are hidden and not necessarily exist. In this case, we put all the features in the both first and second part of the bipartite graph. Then we build connections between features which may share the same concept. For example, if by the domain knowledge we know C1 and C3 may share the same concept X, then we have a connection between C1 and C3 in the bipartite graph. Based on different kind of featuration information come from different sources, we may have multiple bipartite graphs. Then we can combine all these bipartite graphs into one bipartite graph. With more precise domain knowledge featuration information we gain, this bipartite graph can be more related to the real feature relation. Now we are going to show our experimental results. As we said before, our model can work on both supervised learning problem and unsupervised learning problem. So we have experiments on both of the problems. In supervised learning problem, we use three baselines: logistic regressions, k-nearest neighbors, and random forests. We choose following methods as the comparing methods. Multilayer perception, which is the basic deep neural network. Random sparse dropout neural networks. This is a neural network with sparse connections, but the sparse part is randomly decided. The third one is Deep Structured Phenotype Network from 2018. This is also a sparse neural network, and this network also takes advantage from the domain knowledge. The fourth one is combinatorial optimization with graph convolutional networks and guided tree search from Lee 2018. It's a guided tree search algorithm, which is very different from the deep neural network structure we use. The last one is physical informed neural network. It's a neural network with physics information, which is a kind of domain knowledge. In unsupervised learning part, we choose two baselines. The first one is k-means. The second one is hierarchical clustering. We also choose several comparing methods. First one is a plan autoencoder. The second one is network-based stratification from Humphrey 2013. This one is using this algorithm also uses feature relation-based regularization, and it works well in cancer problems. The last one is non-negative matrix tree factorization from Pei 2015. This one is a strong unsupervised learning algorithm. Our methods have three variations: CRBM DNN, GRDNN, and CRBM DNN4. CRBM DNN is the conditional restricted voice machine with deep neural network, but without any regularization. GRDNN is a plain deep neural network with bipartite graph-based regularization. And the CRBM DNN4 is combining the previous two models together. These are the supervised learning experimental results. We test the models on two complex clinical trial datasets. We can see all the baselines, including the plain MLP and the random assigned sparse neural network, all have lower performance, and the state-of-art algorithms have relatively high performance. And our method, the three variations, all have a better performance than those state-of-art algorithms. That shows our use of domain knowledge is very smart. Even some comparing methods also use domain knowledge, but we describe the information from the domain knowledge better than those algorithms. We also get good results on unsupervised learning experiments. We use the cancer dataset from Dana-Farber Harvard to predict the type of cancer and also a high school quiz dataset to predict the grade of the student. Clustering tests are very hard, and these two datasets are very different. So our CRBM DNN model and the GRDN model have different performance in the two experiments. But our full model always gets a better result comparing to the competing method, also baselines. That's all. Thanks for watching. The full photos on the slides are the authors of this paper. If you have any questions, you can contact me. My email is listed on the screen. Special acknowledgement to NVIDIA and NSF